what's fascinating about cosmic inflation is some people have had the idea that what if these different regions of the multiverse, these different parallel universes that we envision in our minds mathematically, what if the multiverse from cosmic inflation gave all of these different universes a place to live? This is a possibility that's exciting and that's worth exploring.
Is there a multiverse?
Welcome to the multiverse, or should I say, our one universe within a multiverse of possibilities. We know that as we approach life, as we move through life, we have many different decisions that we make, not just us, but all things around us, including inanimate things that have quantum outcomes that could have gone many different ways, but only wind up ever occurring in one specific way. Although there's a multiverse of possibilities, we think we're the only one universe out there. But is that actually true? Let's explore. Our idea of the multiverse generally comes about from the notion of quantum mechanics. We think every time we enter into a situation or a setup, there are a whole slew, maybe even an infinity of possibilities that could arise for our outcome. But whenever we make a key measurement or observation, we only ever get one specific outcome. Electrons in a hydrogen atom could be almost anywhere in space, even inside the atomic nucleus itself. But when we make that measurement and we ask the electron with a high energy photon, where are you? We only ever get one specific answer at that moment in time. We then say, well, hey, this is fine. This is a property of quantum mechanics. We have, instead of we're going to get a definitive outcome that we can predict, we only know instead there's a probability distribution of outcomes where we have a whole set of outcomes. Quantum mechanics can tell you how probable each outcome is, but only one thing will ever actually ensue. You have to make that measurement or live through it in order to know which one it is. The multiverse appears in science fiction, in media, in film, in many different ways, often with people experiencing life in one way, then being transported to a different reality where a different set of outcomes occurred. They can pass through from one universe to another. They can travel back in time and alter things in their own universe. From Back to the Future to Primer to Groundhog Day to Everything Everywhere All at Once, the multiverse is a staple of something that occurs in our imaginations. Do not sue us, Marvel Cinematic Universe. And what does this mean in physics terms? Well, for a long time, ideas about the multiverse were really just philosophical. You say, well, there are many ways to interpret the wave function in quantum mechanics, and in what's called the many worlds interpretation of quantum mechanics, you can imagine that all of these universes simultaneously exist. And that whenever an outcome gets made, it sort of tells us, oh, well, we live in this branch of the multiverse rather than any of the other branches. But what's fascinating about cosmic inflation is some people have had the idea that what if these different regions of the multiverse, these different parallel universes that we envision in our minds mathematically, what if the multiverse from cosmic inflation gave all of these different universes a place to live? This is a possibility that's exciting and that's worth exploring. One of the big concepts in physics and mathematics both is the notion of infinity. You know that if something goes on forever, it can approach infinity. And you can have infinity just by counting 1, 2, 3, 4, 5, so on, so on, so on. If you counted for an infinitely long amount of time, you would approach infinity. It's not a number, it's something that goes on and on and on and never ends. It's truly bigger than any number or concept you can imagine. But there's more than one type of infinity. For example, if I said, well, you can go 1, 2, 3, 4, 5, 6 on to infinity, you might say, oh, well, can't I go 2, 4, 6, 8, 10, 12 and get to infinity like that? Sure, you can. It turns out, though, that those two types of infinities are actually the same type of infinity. One is just multiplied by a factor of 2 over the other. You're not getting a bigger infinity by counting by 2s instead of counting by 1s. However, there are several different types of infinities. So 3 different types of infinities that I want people to be aware of come from 1, 2, 3, 4, 5, 6. That's what I'll call a linear or first order infinity. Then I want you to think about exponentials like 2 to the 1, 2 to the 2, 2 to the 3, or 10 to the 1, 10 to the 2, 10 to the 3. That's an exponential infinity. That's what I'll call a second type of infinity. But then I also want you to think of these combinatoric or these factorial types of infinities. 10 factorial, 100 factorial, 1,000 factorial, or different permutations that you can get by combining objects together in sequence, like having a room full of gas molecules colliding together and then picking the winning lottery particle, one after the other in a row. That's a third type of infinity of what I'll call a combinatoric infinity. And a combinatoric infinity is bigger than even an exponential or second type of infinity. In fact, there's a concept called a combinatoric explosion that you get if you say, okay, I have a bag filled with maybe 1 million, maybe 1 billion marbles, maybe even an infinite number of marbles. If I go in and I pull out a marble, what are the chances that I'm going to get a specific marble? Now, if I put the marble back in there and it's going to collide with other marbles, what are the chances that I'm going to pull out all the marbles it collided with? The numbers, the probabilities, they go to infinity. The numbers of itself, they go to infinity very, very rapidly. The probabilities of getting any particular outcome, they go infinitesimal very, very rapidly. There are different types of infinities, and which one you have depends on, in math, the type of mathematical infinity you're considering, and in physics, the type of physical system or process you're considering. When we talk about the multiverse, what we're asking is, if we want this to be physically real, if we want this quantum mechanical multiverse of all of the possibilities we can imagine happening somewhere, if we want that to be physically real, then we need our actual physical universe to at least be big enough to hold all of those possibilities. And in order to know whether it is or not, we have to compare those types of infinity. The infinity you get from a quantum mechanical multiverse with the infinity that's predicted from an inflationary multiverse. If we want to figure out which type of infinity do we have for our quantum mechanical physical universe versus our inflationary multiverse, we have to actually look at what's going on in each of these two systems. If you want a spoiler is The inflationary multiverse is that second infinity type of an exponential infinity, whereas the quantum mechanical multiverse is an infinity of that third type of a combinatoric infinity. So one important concept in quantum mechanics is that things exist, quantum systems exist in a superposition of all possible states until you make a measurement that does something that we call collapses the wave function. And all that means is when you make a measurement, you get one definitive outcome. So I can say there are two types of degrees of freedom. There's something that we call a discrete degree of freedom, where if I have a quantum particle and I say I want to measure this quantum particle's spin, I can measure it in the up-down direction. And I'm either going to find that the quantum particle is spin up or spin down. If I make that measurement and I've got a spin up or a spin down particle, I can then say, well, I'm now going to go and measure it in the left-right direction, in the x direction. And once again, I'll have a 50-50 chance of either it being spin to the left or spin to the right. Every time I make a measurement in a new dimension, x, y, z, I'm destroying the information I made in the previous direction. Quantum mechanical spin is something that is what we call a discrete degree of freedom, but it's discrete in each of the three dimensions that we have. There are also continuous degree of freedom. So if I take a particle of matter like an electron and an antiparticle of matter, a positron, an antimatter counterpart of the electron, and I bring them together, I know what they're going to do. They're going to annihilate into two photons, each of a very specific energy that's given by the rest mass of the electron and positron, E equals mc squared. The energy of those photons is known exactly, but the direction that those photons go off in, yeah, they're going to go off equal and opposite to each other, but will they go off in the x direction, or the y direction, or the z direction, or some combination that makes an angle in any of the three dimensions? That's what we call a continuous degree of freedom. It can take on any of those possibilities. And in our universe, both the discrete degrees of freedom and the continuous degrees of freedom exist in almost all quantum mechanical systems. We have to look at how many particles are there in our observable universe. Our observable universe is pretty big. It goes off for 46 billion light years in all directions and contains somewhere around 10 to the 90 particles, if you include photons, neutrinos, protons, electrons, and every other quantum particle that makes us up. We have had 13.8 billion years since the start of the hot Big Bang for all of these particles to interact with one another, to have a huge variety of potential quantum outcomes. We normally think about the multiverse as something that arises when we make a conscious decision. But in reality, this effect of quantum splitting or having a huge set of possibilities arise for an outcome of a physical system, it happens irrespective of us as well. It doesn't need human intervention. Things that happen in interstellar space, things that happen in the interior of the sun, things that happen when sunlight strikes the surface of the earth, these all lead to a multiverse of possibilities. This is the largest type of infinity possible. When you ask about all of the different possibilities that exist for quantum mechanical outcomes in our universe, you truly get this combinatoric explosion. You get this largest type of infinity of all. So now we have to think about how much actual universe is there, and is it big enough to hold all of these quantum mechanical possibilities? If it is, then the multiverse, as we conceive of it in fiction, could be physically real, even if it's not here in our universe. But if the multiverse from inflation is not big enough to hold all of these possibilities, then this multiverse doesn't exist anywhere but in our minds and in, I guess, what we would call a mathematical rather than a physical space. So let's think about it. I like to think about inflation as you have a plateau. The plateau has an edge. If you roll off the plateau, you roll down into a valley below, and inflation comes to an end. As long as you are on top of the hill, on top of the plateau, inflation is going to continue. But once it falls off the hill and rolls into the valley, inflation comes to an end. Now, we can think about this as a single ball on top of a hill, and maybe it starts off rolling, or maybe something gives it a nudge, and eventually it'll reach the end and roll off, and it'll only happen for a finite amount of time. However, inflation, like all real physical theories, has to also be quantum mechanical in nature. We live in a quantum mechanical universe, and we have no choice but to assume that inflation itself is quantum mechanical. So what happens if I have a quantum mechanical ball on top of a plateau instead of a regular ball? Well, one property of quantum mechanical systems is that their position is inherently uncertain, and that position will spread out like a quantum mechanical wave function over time. So if my ball were rolling very quickly towards one end of the plateau, the quantum spreading that happens would be slow compared to the rolling, and I would only inflate for a certain amount of time, and then I'd roll into the valley below. But if my ball started off rolling slowly, then as it quantum mechanically spread out, there would be a chance that the ball would go closer to the hill. There would be a chance that the ball would just keep rolling slowly as it did in the absence of quantum mechanical spreading. But there's also a chance that the ball would actually go back up towards the center of the plateau, that it would actually move away from the valley on either side. And it turns out, when you work out the mathematics of inflation, the slowly rolling ball is the only option. You cannot have a fast rolling ball, or you do not get enough inflation to reproduce the universe that we see. If the ball rolls slowly, then that means all these different parts of the wave function spread out, and sure, there will be some parts of the wave function that reach the end of the plateau, that roll down into the valley below, and that have, in that once inflating region of space, inflation comes to an end. And when it does, as the ball rolls down into the valley and oscillates, the energy that was inherent to space itself gets converted into matter and radiation, and we get a hot Big Bang. That's great. This happened to us at least once here, 13.8 billion years ago. That's what triggered the end of inflation for us and the start of our hot Big Bang. We have every reason to believe that our observable universe, 46.1 billion light years in radius from where we are, is only a fraction of however large our true unobservable universe is. What about the rest of it? What about the rest of the universe? The universe beyond our observable universe, the universe beyond our bubble of inflation that came to an end. Well, parts of it roll back towards the central part, where they continue to roll slowly, to quantum mechanically spread out, and where parts of it will roll off the plateau, bring it into inflation, and start a new hot Big Bang, while other parts continue to inflate for longer and longer and longer. This sets up a fascinating picture of how we think our inflationary multiverse looks, where we have these large bubbles where inflation ends and hot Big Bangs begin, and you start to get matter and radiation filled universes that have their own quantum mechanical experiences with their own sets of outcomes and a huge variety of possible outcomes. They are separated by more inflating space that drives them all mutually apart from one another. And even though we are constantly getting new regions where inflation ends and the hot Big Bang begins, these two regions where you have a hot Big Bang here and a hot Big Bang there, they never overlap. They never intersect. They never collide with each other, because there's always more inflating space between them that's constantly pushing them apart. How fast do these new universes get created? How many new universes get created? This is something that proceeds at an exponential rate. That's the second type of infinity. It's faster than the 1, 2, 3, 4, 5, 6 infinity, but it's slower than the factorial or combinatoric driven infinity that represents our quantum mechanical universe. So when we say, hey, we've been around for 13.8 billion years with an observable universe full of 10 to the 90 particles that have all been interacting ever since, how many possible outcomes do we have? You can calculate that and you'll get a huge, not infinite, but huge number. It's not infinite because it hasn't been around for an infinite amount of time. We have had all of these particles interacting for all of this time, and it's a large number that's growing. It's tending towards infinity, but it hasn't reached it yet. Same thing, we think, with the inflationary multiverse. How many different possible universes are there in the inflationary multiverse? Well, again, it's a number that's growing. It's growing towards infinity, but it's a smaller infinity. It's going towards infinity more slowly than this larger type of infinity. An exponential infinity is smaller than a combinatoric type of infinity. Does this mean that the multiverse is truly fiction and the inflationary multiverse cannot hold all of the possibilities for our quantum mechanical multiverse that we envision in science fiction and perhaps our imaginations? That's true if inflation hasn't been going on for an infinite amount of time to the past. This picture we drew of a ball atop a plateau that spreads out over time, and where the ball reaches the end of the plateau, inflation ends, but where the ball stays atop the plateau, inflation continues. This will give you a large number of universes that will go to infinity, but it won't go to infinity fast enough to hold all of the quantum mechanical possibilities. The only way that we can say the multiverse is physically real and all these possibilities do exist somewhere, you need one of two things to be true. Either not only will inflation continue in places between different Big Bangs for all of eternity to the future, but inflation must have been going on for an infinite duration to the past. If that is true, if our universe has been undergoing inflation for an infinity of time, then perhaps there really are enough pockets of universe to hold this multiverse of possibilities. The other way that we could still have this be true is if the universe that is inflating was born infinite, that it was born infinite in spatial extent. If that's the case, then it was already infinite when it was born, and there were already enough possible volumes that it could occupy that no matter how many different quantum mechanical outcomes we arrive at, we will have enough physical universe to hold it. We don't know whether either of those things is true or not. All that we have access to in our universe, in our observable universe to look for, is the part of the universe we can observe. And that only corresponds to that final tiny fraction of a second before inflation came to an end and resulted in our hot Big Bang. We don't know the answer to whether there is truly an infinity of worlds out there, but that's what it would take. The universe would have to be truly infinite, either in space or in time, in order for the science fiction quantum mechanical multiverse to be physically real. If our universe is not infinite in size and it has not been inflating for a true eternity, then this quantum mechanical multiverse might be a compelling story, but it's one that falls into the realm of science fiction, not science fact. For as long as humans have been alive on Earth, we've always had regrets, either about things that we did, where we got a bad outcome and we wished afterwards we hadn't done it, or regrets for the things we didn't do and the chances we didn't take and the times we chickened out and we had an opportunity and we didn't seize it. How many of us have wondered what if about some aspect of our life? What if I had been brave and gone for the low likelihood but high risk, high reward opportunity? What if I had attempted to kiss the one who got away at the end of the night instead of letting them get away? What if I had been bold and took a chance on myself instead of taking the safe route that led me to a known but low reward outcome? Most of us will never know what that's like. The multiverse is fascinating because it gives us that extra hope that perhaps somewhere out there is the version of me who took the chance, who took the risk, who went for it, who got the reward. But unless our universe is bigger or older than we have any way of ever finding out about, it's not something that's physically real. Unless the universe is truly infinite, either in time to the past or truly infinite in spatial extent, there simply isn't enough universe to hold all of those quantum mechanical possibilities in a physical way. That doesn't mean the many worlds interpretation of quantum mechanics is invalid, but it means that there is no physical universe out there where you lived your life without the regret you carry with you today. What this means is that in all of the multiverse, as vast as it is, there's only you. There's only this one version of you with the one life you've led up to this point, with the one opportunity to live your life to the fullest with the rest of it that remains. And I encourage you to do exactly that.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.